Okay, today we're going to review some basic chemistry terms that theoretically you should already be familiar with when you take AP Biology, but from what I've seen, most people, if they haven't had chemistry in a while, they may be a little rusty, so we're going to walk through all of these terms. So these are the vocabulary terms that we're going to be discussing in this chapter, the difference between atoms and compounds, the parts of an atom, what an ion is and what an isotope is, how to properly write the symbols for atoms showing the atomic number and the mass number, the difference between different kinds of bonds, what a redox reaction is, and how to calculate pH and what pH tells us about acids and bases. So, a few things. First, the simplest matter that exists would be the element. You can't get simpler than an element. When elements combine, they form compounds. If you think of elements, think of the periodic table. Hydrogen, oxygen, gold, silver, platinum. These are all elements. And the simplest piece of an element is an atom. You cannot get smaller than an atom and retain the properties of the element. For example, you could have gold, one atom of gold and one atom of hydrogen, and they would be very, very different from each other. They have specific properties. But if I take a proton from hydrogen and a proton from gold, the protons would be identical. Because once we go smaller than an atom, protons, neutrons, and electrons are all the same no matter which element they are in. So, what makes each element specifically unique is going to be the number of protons. I can have carbon with different numbers of electrons. I can have carbon atoms that have different numbers of neutrons. But I cannot have carbon atoms with different numbers of protons, because if I add a proton to carbon, it's not carbon anymore, it's nitrogen. And if I take a proton away from carbon, it's not carbon anymore. Now it's boron. So the number of protons is specific and makes an element have its properties. The three parts of an atom you should be familiar with. Protons and neutrons are found in the nucleus, in the center of the atom. Protons have a positive charge, neutrons do not have a charge. And then electrons are found outside the nucleus in what we sometimes call the electron cloud. Technically, they're arranged in levels, which you should have learned in chemistry, but we're not going to be discussing that in detail. You do need to know what valence electrons are, though, and those are those outermost electrons, and you should know that those are the ones that will determine the chemical properties of the atom. Atoms generally want to have 8 valence electrons, which is why your noble gases are typically unreactive. They don't react with each other because they already have 8 valence electrons. Other elements off the periodic table will either gain, lose, or share electrons in order to have 8 in their outer shell. Something you probably would not have discussed in chemistry, one application to life, would be the fact that we are actually made of just 4 main elements: carbon, hydrogen, oxygen, and nitrogen. They compose over 98% of our bodies. Why? Because we're made of, think of the things we're made of. We're made of water, which is hydrogen and oxygen. We're made of proteins and fats, carbohydrates, and then DNA and the nucleic acids. And those things are all made of carbon, hydrogen, and oxygen, and some of them also include nitrogen. So if you can remember CHON, you can remember the 4 main elements in living things. Some books will also add phosphorus and sulfur, and when we get to the biochemistry chapter, you'll see why those 2 are also extremely important, but they're not as common as the other 4. Trace elements are what we call elements that we need in very small quantities. We only need traces of them. So for example, iodine, chromium, and selenium, you don't have to memorize those. But what you get in, for example, a daily vitamin are probably a lot of your trace elements. If you don't take vitamins, but you eat vegetables, spinach, and things like that, a lot of your trace elements come from those things that you eat. So for example, iodine, you need such a tiny amount, 150 micrograms. A microgram is a millionth of a gram. So if you think of a gram as about the weight of a paperclip, so the millionth of the weight of a paperclip is the amount of iodine you need per day. In fact, large amounts are toxic to you. But if you have a deficiency in iodine, you end up with what's called hypothyroidism, and you can get a goiter, like the picture here with this man. It's a swollen thyroid gland. What you're not going to really see in this country are these kinds of deficiency diseases. You may have heard of them maybe from history class, like scurvy. Pirates would eat lemons to prevent scurvy. It was a lack of vitamin C. Or there's pellagra, beriberi, rickets. These are all vitamin deficiency diseases when a person doesn't get enough trace elements. But in this country, because we tend to have plenty of food and a lot of enriched foods and breads and grains and vegetables, we don't really see those kinds of diseases here, mainly in third world countries where people are not getting enough food. So be aware what a trace element is. All right, going back to atoms. So the vocabulary you should know, the atomic number is what goes in the bottom left, and it's the number of protons in an atom. And the mass number is the number of protons and neutrons added together. So the full symbol, for example, might look like this. It's 12, 6, carbon. This is our number of protons, and this is our protons plus our neutrons. From this, if you were asked how many neutrons are in carbon 12, which is what the name of this carbon would be, you would just subtract 12 minus 6, and carbon 12 would have 6 neutrons. And we can do the same for carbon 14. Carbon 14, you'll notice, still is going to have 6 protons, but 14 minus 6, it's going to have 8 neutrons. These are called isotopes. It'll come up in a couple of slides. Elements with the same number of protons but different numbers of neutrons. And this is very common in nature. Again, the number of protons, notice, does not change, or else you end up with a different element. So this is the proper way of writing that symbol. The atomic mass is what you usually see on the periodic table. So if I was to look up carbon on the periodic table, I'm not going to see all of those carbon 12 and carbon 14. What I'm going to see is a big C, a 6, and probably a decimal number like this. So the decimal is called the atomic mass. It's the average of all the isotopes in nature. And it's based on how common the isotopes are. So for example, carbon 12 is one isotope of carbon. It has a certain number of neutrons. That's what makes it an isotope. This is a different isotope of carbon, and carbon 14 is a third isotope of carbon. Again, an isotope is when they have different numbers of neutrons. If I asked you which one of these three must be the most common isotope, well, since the periodic table shows the atomic mass, and the atomic mass is calculated by how common the isotopes are, an atomic mass of 12.011 would tell me that carbon 12 must be the most common isotope, because when I take the average of all of them in nature, the average mass of a carbon is closest to 12. So again, the atomic mass is a decimal. The mass number is the actual number of protons and neutrons in a specific isotope of an atom. The notation that I've been writing is called AZ notation, and you don't have to know that that's what it's called, but you definitely need to know how to write it, and you need to know how to figure out protons, neutrons, and electrons from it. So again, if I know the atomic number, for example, for carbon 12 is 6, and I know that its mass number is 12, I can figure out how many neutrons it has, 12 minus 6, and it would have 6 neutrons. Additionally, I could go the other way. I could tell you how many neutrons and protons something had, and you could write the AZ notation that way. For example, if I told you, let's say nitrogen, and I told you that it had 7 protons and let's say 8 neutrons, and I said to write the AZ notation, you would do this. N for nitrogen, it has 7 protons, and then I would add my protons and neutrons, and this would give me my mass number, and this would be my AZ notation. Now technically charges would also go on here, but we'll talk about charges later. Okay, and so here are 2 practice ones. Now I wrote here to write the AZ notation including the mass number and the atomic number, and I said to base it on the most common isotope. So we're going to pretend like, even though this is 24.305, we're going to assume that we're writing it for magnesium 24, the most common isotope. And for this one, we're writing it for chlorine 35, the most common isotope. So again, we would only use whole numbers for these, and I'm guessing that that's the most common isotope because the number rounds closest to that. So in our bottom corner for magnesium, it would be our atomic number, 12, our number of protons. And in our top corner, it would be 24 because that would be our protons plus our neutrons for our most common isotope. If you were then asked how many neutrons does this have, 24 minus 12, 12 neutrons. And then for our second one, this would be chlorine 35 is what this would be called. We would put our 17 here, that's our protons. 35 up here, that's our mass number. And if you were asked how many neutrons does this have, 35 minus 17 gives us 18 neutrons. So that's how you would write a Z notation from a periodic table square. Again, technically, I was guessing at the most common isotope. There are actually multiple isotopes of both of these. I know chlorine has two, chlorine 35 and chlorine 37, but we're sort of simplifying. All right, in chemistry, you would have talked about isotopes, and again, the definition, here's your actual definition. An isotope is an atom that has the same number of protons, same element, but a different number of neutrons. And again, most elements have multiple isotopes in nature. The example we've been using is carbon. Carbon has carbon 12, carbon 13, and carbon 14. In chemistry, like I said, you would have talked about isotopes. You probably would have even had to calculate atomic masses and some things like that. But I don't know that in basic chemistry class you ever really talk about using isotopes or why they're important. So in biology, isotopes are extremely important. There are actually some real-world applications that are biological. One of them, well, a lot of them, have to do with specifically radioactive isotopes. So a radioactive isotope is an isotope that has extra neutrons that makes the nucleus unstable. So it's usually because there's too many neutrons, and the nucleus literally is unstable. What does that mean? It means that that nucleus will actually decay. It will actually break down and give off radiation. And it's a nuclear reaction, so in certain types of radioactive decay, the element actually undergoes a nuclear change to where it turns into another element. Now, you don't have to know the details about types of radioactive decay, but you do need to know that if an isotope is radioactive, like carbon-14, it'll break down, and not only does it break down, but it breaks down at a rate that we know, and that rate's called a half-life. The half-life is unique to each element. So for carbon-14, the half-life is 5,730 years. So what that means is if you were to have a fossil that died, an organism that died, and had some amount of carbon-14 in it, when 5,730 years went by, about half of that carbon-14 would have decayed into nitrogen. And when another half-life, or another 5,730 years go by, there would only be about a quarter of it left. In other words, half of what was left would now be gone. And so over time, these would just continue to decay until there was so little left you couldn't even use it. And so the fact that we know how quickly they break down means that if we dig up a fossil, we can figure out how old it is. So we can actually figure out how old a fossil is by how much carbon-14 is still left and how much has decayed into nitrogen. Now, carbon-14 is not the only one. In fact, you can't even use carbon-14 to date something like dinosaur bones because its half-life is too short. After about 40,000 years, there's not enough left to measure. But there's lots of radioactive isotopes, and they all have different decay rates, and we know what those decay rates are. So we can date dinosaur bones using other radioactive isotopes that decay more slowly. And in the lab, they might use radioactive isotopes that decay very fast, that decay in minutes or even in seconds to time certain reactions. So why do we care about radioactive isotopes in biology? Well, I mentioned one reason. One of them is that we can use them to date fossils because of their decay. And the other things we use them for are medical. We can use them as tracers. You could actually inject them into, for example, somebody has a heart attack. They can inject radioactive iodine into their veins, and it will actually light up the blood vessels in their heart, and they can actually find the blockage. And then rather than doing open heart surgery, they can actually go in and put in a stent or open up that blockage, and the person goes home the next day rather than cracking their chest open and they have a long recovery. So that's how we use them as tracers. There's a radioactive barium they use to find ulcers. You drink it, and they take X-rays, and you literally light up. They can also treat tumors using radiation. For example, they can treat prostate cancer by putting a radioactive pellet in the prostate, and the radioactivity kills the cancer. Here's just some pictures to wrap it up. This is a half-life, not on the test. It's just showing how it decays. And here's some pictures of an angiogram and a PET scan, and how the radioactive isotopes light things up.